October 28th, 2025, 3:42 p.m. Greenwich Mean Time. Dr. Sarah Chen sat in her cramped office at the Space Telescope Science Institute in Baltimore, staring at a number on her screen that shouldn't exist. The James Webb Space Telescope had just completed its thermal imaging scan of 3I Atlas, the interstellar visitor that had captivated astronomers for the past 4 months. The mid-infrared instrument, MIRI, had been pointed at the comet during its journey away from perihelion, capturing detailed temperature readings across its surface. And those readings were impossible. 373 Kelvin on the sunlit side. That's 100 degrees Celsius. Hot enough to boil water if water could exist in the vacuum of space. At 203 million kilometers from the sun, roughly 1.5 times the distance between Earth and our star, the expected temperature should have been somewhere around negative 73 degrees Celsius. 200 degrees colder than the frozen wastelands of Antarctica. Yet here was this ancient wanderer from beyond our solar system, glowing with heat that defied every model, every equation, every comfortable assumption about how matter behaves in the cosmos. Sarah had seen anomalies before. She'd spent 15 years analyzing data from space telescopes, watching distant galaxies, examining exoplanet atmospheres, mapping the surfaces of asteroids and comets. Anomalies were part of the job. Usually they resolved themselves into measurement errors, calibration issues, or misinterpreted data. But this one felt different. This one made her spine tingle with that peculiar mixture of excitement and dread that comes when you realize you're looking at something that might rewrite the textbooks or destroy your career, depending on whether you're right or wrong about what you're seeing. She picked up her phone and called Marcus Weber at the European Space Agency. It was late evening in Europe, but Marcus was known for working odd hours, especially when something interesting was happening. He answered on the second ring. "Please tell me you're seeing what I'm seeing," Sarah said without preamble. There was a pause, then Marcus's voice, careful and measured. "If you're seeing thermal readings that are 400 degrees higher than they should be, then yes, I'm seeing exactly what you're seeing. I've recalibrated 3 times. I've checked the instrument status. I've compared it against calibration targets. Sarah, the instruments aren't broken." That's when Sarah Chen knew that October 28th, 2025 would be remembered. Because when your instruments are working perfectly and they're telling you something impossible, you're either witnessing the birth of a discovery or standing at the edge of a mystery that might never be solved. And right now she couldn't tell which. The thing about temperature in space is that it's surprisingly predictable. Not like weather on Earth, where 1,000 variables interact in chaotic ways to produce surprises. In the vacuum of space, temperature follows simple, elegant rules. You receive energy from the sun in the form of radiation. That energy warms your surface. You radiate that energy back into space in the form of infrared light. The balance between incoming and outgoing energy determines your temperature. It's physics so fundamental that we teach it to undergraduates, so well tested that we use it to design spacecraft thermal control systems, so reliable that we can predict the temperature of distant objects with remarkable accuracy. At 203 million kilometers from the sun, the solar energy flux hitting 3I Atlas should be about 550 watts per square meter. For comparison, that's roughly half the intensity of sunlight hitting Earth's surface on a clear day. Not nothing, but not enough to create warmth. A dark surface, something that absorbs most of the sunlight, might reach temperatures around negative 40 degrees Celsius. A bright, reflective surface would be colder still, perhaps negative 80 degrees Celsius. The exact number depends on the surface material, its color, its texture, how efficiently it radiates heat back into space. But there are limits, hard limits set by the laws of thermodynamics. You cannot be hotter than the energy you're receiving allows unless you have another energy source, and 3I Atlas was 400 degrees past that limit. Let me give you some context for what that means. Comet 67P, the one that the Rosetta spacecraft visited and studied in exquisite detail, maintained surface temperatures around negative 70 degrees Celsius when it was at similar distances from the sun. Europa, Jupiter's ice-covered moon, sitting in the weak sunlight of the outer solar system, maintains surface temperatures around negative 160 degrees Celsius. Even Mercury, the closest planet to the sun, only reaches 430 degrees Celsius on its sun-baked side, and that's because it's receiving sunlight 50 times more intense than what reaches 3I Atlas. Yet here was this visitor from another star system, this 10-billion-year-old relic from the ancient universe, maintaining a balmy 100 degrees Celsius, warm enough that if you could somehow stand on its surface in a perfectly insulated suit, you'd feel tropical heat radiating from the ground beneath your feet. Warm enough to sublimate any water ice, to drive chemical reactions, to glow visibly in the infrared. Warm enough to be utterly, completely, devastatingly impossible, given the amount of sunlight it was receiving. Sarah spent the next 18 hours doing what scientists do when confronted with impossible data. She checked everything. She pulled up the calibration files for JWST's MIRI instrument, examining every coefficient, every correction factor, every algorithm that transformed a raw detector counts into temperature reading. She contacted the instrument team, the people who had spent decades designing and building MIRI, asking them to review the data independently. She compared the 3I Atlas observations against other targets observed the same week, verifying that JWST was measuring temperatures correctly for objects where we knew what the temperature should be. Everything checked out. The instrument was working perfectly. The calibration was correct. The temperature measurement was accurate, which meant the impossible reading was real. But Sarah Chen wasn't the only person staring at impossible data that week. On September 14th, 2025, 6 weeks earlier, the Hubble Space Telescope had captured thermal observations of 3I Atlas during one of its scheduled monitoring sessions. At the time, the temperature readings had seemed odd, elevated above expectations, but not dramatically so. The data had been flagged as potentially problematic, possibly contaminated by background sources or affected by instrumental artifacts. The Hubble team had made a note to review it later, but with dozens of targets to observe and limited telescope time, that particular anomaly had been shelved, waiting for someone to have time to investigate properly. Now, with JWST's data confirming the high temperatures, someone pulled those Hubble observations out of the archive, and there it was. Clear as day once you knew what you were looking for. The same thermal excess. The same impossible heat signature. Hubble had seen it too. Two completely independent space telescopes using different instruments, different detectors, different calibration methods, both measuring the same thing. This wasn't an instrumental artifact. This wasn't a measurement error. This was real. And then someone remembered the SOHO spacecraft, the Solar and Heliospheric Observatory, stationed at the L1 Lagrange point between Earth and the Sun, continuously monitoring our star's activity. SOHO wasn't designed to study comets in detail, but its coronagraphs occasionally captured images of bright comets passing near the Sun. In August 2025, SOHO had observed 3I Atlas during its approach to perihelion, capturing it in several of its images. Those images weren't high resolution, weren't intended for thermal analysis, but they contained information nonetheless. Brightness, color, the way light scattered off the comet's surface. A team at the Naval Research Laboratory in Washington, D.C., the group that operates SOHO's LASCO coronagraphs, went back through the August data with new eyes. They extracted every image containing 3I Atlas, performed photometric analysis, compared the brightness to theoretical models, and they found something that had been overlooked in the initial analysis. The comet was too bright in certain wavelengths. Specifically, it was emitting more thermal infrared radiation than it should have been based on its distance from the Sun. The excess had been there all along, visible in the data, but dismissed as noise or attributed to the comet's unusual composition. Now, with 3 independent confirmations from 3 different telescopes spanning August through October, a pattern emerged. 3I Atlas had been abnormally hot since the moment we first started paying attention to its thermal properties. This wasn't a sudden event, wasn't a flare or outburst. This was sustained, continuous, persistent excess heat. For at least 3 months, possibly longer, this object had been pumping out more thermal energy than it was receiving from the Sun. The scientific method has a way of dealing with observations that contradict expectations. You generate hypotheses, possible explanations for what you're seeing. Then you test those hypotheses against the data, eliminating the ones that don't fit, refining the ones that do, until you converge on an answer that explains everything. It's a process that has worked remarkably well for 400 years, taking us from ignorance to understanding across every domain of human knowledge. So that's what Sarah and her rapidly growing team of collaborators did. They generated hypotheses. Hypothesis 1 was the most obvious and the most comforting. Measurement error. Maybe all 3 telescopes were wrong. Maybe there was a systematic error in how we measure temperatures of distant objects. Maybe the algorithms that convert brightness into temperature readings contained a flaw that no one had noticed before. It wasn't impossible. Science has a history of accepted techniques that turned out to be subtly wrong, producing measurements that were systematically biased. It would be embarrassing, certainly, to discover that space-based thermal measurements were unreliable, but it would be fixable, understandable, safe, except the math didn't work. JWST, Hubble, and SOHO use completely different methods to measure temperature. JWST's MIRI observed in the mid-infrared, measuring the peak wavelength of thermal emission and using Wien's displacement law to calculate temperature. Hubble used its Wide-Field Camera 3 to measure thermal emission in near-infrared bands, using the ratio of brightnesses at different wavelengths to infer temperature. SOHO's LASCO coronagraphs measured total brightness and compared it to models of expected reflectivity. 3 different techniques, 3 different mathematical approaches, 3 instruments built by different teams using different technologies. And they all agreed. If they were all wrong, they'd have to be wrong in exactly the same way, biased by exactly the same amount. That's not how measurement errors work. Hypothesis 2 suggested that maybe 3I Atlas had an extremely dark surface, something that absorbed sunlight with unusual efficiency. If the surface were coated with material darker than coal, blacker than asphalt, it might absorb enough solar energy to achieve higher temperatures than expected. We know such materials exist. Carbon nanotubes can be grown in laboratories that absorb 99.9% of incoming light. Maybe some natural process had coated this ancient comet with ultra-dark material. The physics of this hypothesis were at least plausible. A perfectly black surface at 3I Atlas's distance from the Sun could potentially reach temperatures 50 or 60 degrees higher than a typical gray surface. But 50 degrees wasn't 400 degrees. To achieve temperatures of 100 degrees Celsius, the surface would need to absorb every single photon of sunlight and somehow prevent any of that energy from radiating away. That violates the Stefan Boltzmann law, which governs how hot objects emit thermal radiation. The hotter something gets, the more efficiently it radiates energy away. There's a natural ceiling, a maximum temperature you can reach with a given amount of incoming energy. And 3I Atlas was way past that ceiling. Plus, if the surface were that dark, we'd see it in the visible light observations. The comet would appear extremely dark, barely reflecting any sunlight, but visible light observations from ground-based telescopes showed 3I Atlas to have normal, even somewhat bright reflectivity. Its surface wasn't unusually dark. This hypothesis failed. Hypothesis 3 ventured into more exotic territory. Maybe 3I Atlas contained radioactive isotopes in unusual concentrations, materials that were generating heat through nuclear decay. We know this happens. The Earth's interior remains hot partly because of heat generated by the decay of uranium, thorium, and potassium in the mantle. Radioisotope thermoelectric generators use plutonium-238 to power deep space probes. Could 3I Atlas be loaded with radioactive materials, warming itself from within through the steady release of nuclear energy? The math on this one was at least calculable. To generate the observed heat output, roughly 2.4 gigawatts of continuous power, you'd need an extraordinary concentration of short-lived radioactive isotopes. And here's the problem with that. Short-lived isotopes decay quickly, that's why they produce a lot of heat, but they also disappear quickly. There are no natural radioactive materials with half-lives long enough to remain active after 10 billion years, while producing gigawatts of power. The longest-lived heat-producing isotope we know of is uranium-238, with a half-life of 4.5 billion years. After 10 billion years, any uranium-238 that existed when 3I Atlas formed would have gone through more than 2 half-lives, reducing its heat output to less than a quarter of its original value. And uranium-238 doesn't produce that much heat to begin with. But there was a more direct way to test this hypothesis. Radioactive decay produces gamma rays, high-energy photons that would be detectable by the Fermi Gamma Ray Space Telescope. If 3I Atlas were loaded with radioactive materials generating gigawatts of power, it would be blazing in gamma rays. In early October, an astronomer at the Naval Research Laboratory checked Fermi's database, looking for any gamma ray detections from 3I Atlas's position. Nothing. The Fermi telescope had been looking at that region of sky multiple times between July and October as part of its all-sky survey. If there were significant gamma ray emissions, Fermi would have seen them. The absence of gamma rays ruled out radioactive decay as a significant heat source. Hypothesis 4 suggested chemical reactions. Maybe volatile materials trapped inside 3I Atlas were undergoing exothermic chemical reactions, releasing stored chemical energy as heat. We see this in terrestrial systems. A compost pile generates heat through the chemical breakdown of organic matter. Certain minerals release heat when they react with water. Could some exotic chemistry be warming this comet from within? The problem with this hypothesis is energy budget. Chemical reactions release energy that was originally stored in chemical bonds when those molecules formed. The total amount of energy you can extract is limited by the chemical composition of your material. To generate 2.4 gigawatts continuously for 4 months, the observed duration of the thermal anomaly, you'd need to be consuming about 1,600 megawatts worth of chemical reactants every second. That's an enormous amount of material. We're talking about thousands of tons of reactive chemicals being consumed every day. And those reactions would produce byproducts, gases, and molecules that would show up in spectroscopic observations. But the spectroscopy of 3I Atlas's outgassing showed normal cometary compounds, water vapor, carbon dioxide, cyanide, with the addition of that unusual nickel emission. No exotic reaction products, no sign of the massive chemical processing that would be necessary to explain the heat output. By October 30th, 2025, Sarah Chen's inbox had exploded with messages from colleagues around the world, all asking variations of the same question. What the hell is going on with 3I Atlas? A hastily organized Zoom call brought together 50 astronomers from a dozen countries, crowding into virtual conference rooms to discuss the impossible comet. And that's when someone mentioned the thermal map. JWST's MIRI instrument doesn't just measure the overall temperature of an object. It creates maps, showing how temperature varies across the surface. For most celestial bodies, these thermal maps are boringly predictable. The side facing the sun is hot, the side facing away is cold. The poles which receive sunlight at a grazing angle are colder than the equator. It's simple geometry, simple physics, and it works for everything from Mercury to Mars to distant asteroids. Except 3I Atlas. The thermal map made no sense whatsoever. The hottest regions weren't on the sun-facing hemisphere where solar heating was strongest. They were at the poles. The shadowed poles, the regions receiving the least amount of direct sunlight. And the coldest regions, the areas showing the lowest temperatures, were near the equator on the sun-facing side, exactly where they should have been hottest. The temperature. Distribution was inverted, backwards, completely contrary to what happens on every natural object we've ever observed. Dr. James Park from Caltech was the first to articulate what everyone was thinking. This looks like internal heating. The object is warm from the inside, not from the outside. The heat is coming from the interior and radiating outward, which is why the poles are hot. They're the most efficient heat radiators because they have the highest surface area to volume ratio at the ends of a rotating body. Someone asked the obvious question. What natural process creates internal heating in a comet? The answers came slowly, haltingly, each one immediately followed by reasons why it couldn't work. Tidal heating, the process that keeps Jupiter's moon Io volcanically active, requires a nearby massive body to gravitationally squeeze and flex the object. 3I Atlas was alone in space, far from any planet. Gravitational compression heating requires enormous mass, enough to create internal pressures that generate heat. 3I Atlas, at roughly 30 billion kilograms, had nowhere near sufficient mass. Magnetic induction heating requires changing magnetic fields. There were no strong magnetic fields in interplanetary space at 3I Atlas's location, and observations had failed to detect any magnetic field around the comet itself. The list of natural heating mechanisms was short, and none of them applied, which left the group staring at an object that was somehow generating internal heat without any apparent mechanism to do so. The silence on the Zoom call stretched uncomfortably long until Dr. Sofia Ramirez from Harvard broke it with a statement that would soon be quoted in a dozen news articles. Either we're witnessing physics we don't understand, or we're witnessing engineering we don't recognize, and I'm not sure which possibility is more disturbing. But the thermal map wasn't the only anomaly revealed by the October observations. When you study an object over time, watching how it changes, patterns emerge that single snapshots can't show. Between July and October 2025, 3I Atlas had traveled from roughly the orbital distance of Mars, through perihelion at 203 million kilometers from the Sun, and was now moving back outward past Mars's orbit again. Its distance from the Sun had varied significantly. On October 2nd, when it passed near Mars, it was at a distance where solar heating should have warmed it to perhaps negative 30 degrees Celsius. On October 29th, at perihelion, it reached its closest approach, where temperatures might have climbed to around negative 10 degrees Celsius. Now in late October, as it moved away from the Sun again, it should be cooling back down toward negative 40 or negative 50 degrees. That's how comets behave. Their temperatures track their distance from the Sun with predictable regularity. When Comet 67P was studied by Rosetta, its temperature rose and fell in lockstep with its solar distance, following curves that match theoretical predictions almost perfectly. It's one of the most reliable relationships in cometary science. 3I Atlas violated that relationship completely. The temperature data from July through October showed remarkable stability. On October 2nd near Mars, JWST measured 365 Kelvin. On October 29th at perihelion, follow-up observations measured 380 Kelvin. On October 30th, as it moved away from the Sun, the temperature had dropped slightly to 370 Kelvin, a total variation of only 15 degrees across a distance change that should have produced variations of 50 degrees or more. The temperature curve was nearly flat. The object maintained an almost constant temperature regardless of how much sunlight it was receiving. Dr. Emily Rodriguez from MIT ran the statistical analysis. For a body with the surface properties inferred from visible light observations, the probability of maintaining such stable temperatures across that range of solar distances was less than 0.1%. You'd need an internal heat source that exactly compensated for variations in solar heating, ramping up when solar input decreased, ramping down when solar input increased, maintaining thermal equilibrium with remarkable precision. That's not how natural objects behave. That's how thermostats behave. And then there was the cooling rate problem. After perihelion, as 3I Atlas began its journey back to the outer solar system, it should have started cooling rapidly. The physics of thermal radiation described by Newton's law of cooling predicts that hot objects cool at a rate proportional to their temperature difference with their surroundings. Space is cold, effectively at 3 Kelvin, the temperature of the cosmic microwave background. An object at 380 Kelvin in that environment should dump heat into space at a furious rate. Cooling by dozens of degrees in the first few days after its heat source, the Sun begins to diminish. 3I Atlas cooled by 10 degrees in the first week after perihelion. Not the expected 50 degrees, not even close. It was shedding heat far more slowly than physics predicted, as if something inside were continuing to supply warmth, compensating for the radiative losses. Dr. Rodriguez calculated the probability of this cooling rate occurring naturally in an object with 3I Atlas's observed property, 0.3%, another impossibly unlikely result. The spectral analysis added yet another layer of strangeness. When you measure the spectrum of thermal radiation from an object, the shape of that spectrum tells you about the temperature. Hot objects emit most of their energy at shorter wavelengths. Cooler objects emit at longer wavelengths. This relationship, described by Planck's law of blackbody radiation, allows us to determine temperature by measuring where the emission peaks. JWST's MIRI instrument measured the thermal emission spectrum of 3I Atlas with exquisite precision, capturing data across wavelengths from 5 to 28 micrometers. The spectrum showed a clear peak at 7.8 micrometers, corresponding to a temperature of 373 Kelvin, exactly matching the direct temperature measurement. But here's what bothered Dr. Chen when she examined the spectrum in detail. The shape was too perfect. Real objects aren't perfect blackbodies. Their surfaces have texture, composition variations, areas that emit more efficiently than others. When you measure the thermal spectrum of a comet, you typically see a jagged, irregular curve with emission lines from specific molecules. absorption features from minerals, deviations from the ideal blackbody shape. The spectrum of 3I Atlas was smooth, almost perfectly matching the theoretical blackbody curve for an object at 373 Kelvin. It looked engineered, like something designed to emit thermal radiation with maximum efficiency. Dr. Park noted that the only surfaces that produce such clean blackbody spectra are those specifically designed to do so. Cavity radiators, devices used in laboratories as calibration standards, produce perfect blackbody spectra because they're shaped to trap light, forcing it to bounce around inside until it reaches thermal equilibrium. The fact that 3I Atlas's spectrum was so clean suggested either an incredibly uniform surface composition or a surface geometry that somehow mimicked the behavior of an artificial cavity radiator. Neither explanation was comforting. And then there was the connection to the blue light, the visible wavelength anomaly that had been observed during the approach to perihelion. Multiple observers had reported that 3I Atlas appeared unusually blue. Bluer than typical comets, bluer even than the sun itself when viewed through appropriate filters. For an object to appear blue, it must emit more light at shorter wavelengths than at longer wavelengths. That requires high temperatures. The sun appears yellowish-white because its surface is at 5,800 Kelvin. Objects that appear blue are hotter, with surface temperatures above 6,000 Kelvin. But the thermal infrared measurements showed 3I Atlas at only 373 Kelvin. These two temperature measurements were incompatible. You can't have a surface that's simultaneously 373 Kelvin in the infrared and 6,000 Kelvin in the visible, unless there are two separate sources of light, unless the visible blue glow is coming from something other than simple thermal emission, unless whatever is generating heat inside this object is also producing high-energy photons through some non-thermal mechanism. Dr. Ramirez suggested fluorescence as a possible explanation. Certain molecules absorb ultraviolet light from the sun and re-emit it at visible wavelengths, producing colors that don't correspond to the object's actual temperature. But fluorescence is a faint effect, producing subtle glows, not the bright blue emission that was being observed. And fluorescence has specific spectral signatures, narrow emission lines at characteristic wavelengths. The blue light from 3I Atlas appeared continuous, broadband, more consistent with thermal emission from a hot source than with fluorescent processes. The cumulative statistical probability of all these anomalies occurring together in a natural object was becoming absurdly small. Dr. Rodriguez compiled the numbers during a sleepless night in early November. The stable temperature across varying solar distances, less than 0.1% probability. The slow cooling rate, 0.3% probability. The perfect blackbody spectrum, conservatively estimated at 0.5% probability. The inverted thermal map with hot poles, perhaps 0.2% probability. The blue light emission inconsistent with thermal infrared temperature, another percent probability. Multiply these independent probabilities together and you get one chance in 33 million. Those are not good odds for a natural explanation. But the most compelling piece of evidence came from an unexpected source. On October 15, 2025, the Subaru telescope in Hawaii had captured a high-resolution thermal image of 3I Atlas using its cooled mid-infrared camera and spectrometer. Subaru's 8.2-meter mirror and advanced adaptive optics system allowed it to resolve details on the comet's surface that space telescopes couldn't match. The resulting image showed something that made every astronomer who saw it pause and stare. There were distinct hotspots on the surface, 12 of them, each approximately 40 to 60 degrees hotter than the surrounding terrain. And these hotspots weren't randomly distributed. They were arranged in a pattern, spaced evenly around the comet's surface, forming a geometric arrangement that looked almost crystalline in its regularity. Dr. Chen spent an entire day analyzing that image, measuring the positions of the hotspots, calculating their distribution. She tried every statistical test she could think of to determine whether the pattern could be random. She compared it to Monte Carlo simulations of random point distributions on spherical surfaces. She calculated clustering coefficients, nearest neighbor distances, spatial correlation functions. Every test came back the same way. The probability of 12 points being randomly distributed on a sphere and showing this level of geometric regularity was less than 1 in 100,000. The hotspots were arranged deliberately, or at least according to some organizing principle that wasn't random chance. Each hotspot was circular or hexagonal in shape, with diameters ranging from 200 to 400 meters. They maintained constant temperatures about 50 degrees above the ambient surface temperature, showing no variation that corresponded to the day-night cycle of 3I Atlas's rotation. They weren't correlated with surface features visible in optical images. They didn't correspond to areas of active outgassing. They just sat there, 12 warm circles on the surface of an ancient comet, pumping out heat for no apparent reason. When Dr. Park saw the Subaru image, he immediately thought of heat exchangers, the kind of engineered devices used to manage thermal loads on spacecraft. The regular spacing would maximize coverage while minimizing interference between adjacent heat radiators. The circular or hexagonal shapes would optimize surface area for radiation. The constant temperature would suggest active thermal management, something regulating the heat flow to maintain set points. He didn't say any of this out loud during the group discussion, but he thought it, and he knew others were thinking it too. The energy budget calculation was damning in its simplicity. The Stefan-Boltzmann law describes how much power an object radiates as thermal energy based on its temperature and surface area. For a sphere 5 kilometers in diameter at a temperature of 373 Kelvin, that equation gives you a straightforward answer. The object is radiating approximately 2.4 gigawatts of power into space. That's not a small amount. That's the output of a large nuclear power plant. For comparison, the Palo Verde Nuclear Generating Station in Arizona, the largest nuclear plant in the United States, produces about 3.3 gigawatts of electrical power. Now calculate how much power 3I Atlas is receiving from the sun at its current distance. The solar constant at Earth's orbit is about 1,260 watts per square meter. At 3I Atlas's distance of 203 million kilometers, the solar intensity drops to roughly 550 watts per square meter. The cross-sectional area of a 5-kilometer sphere is about 20 square kilometers. Multiply that by 550 watts per square meter, and you get about 800 megawatts of incoming solar power. The object is radiating 2.4 gigawatts. It's receiving 0.8 gigawatts. The deficit is 1.6 gigawatts, or 1,600 megawatts. That's the amount of power that must be coming from somewhere other than the sun. That's the power output that has no natural explanation. Over the 4-month observation period from July through October, 3I Atlas radiated approximately 16.6 trillion joules of excess energy above and beyond what it received from the sun. To put that in perspective, that's equivalent to 4 megatons of TNT, roughly 200 times the energy of the Hiroshima bomb. Or looked at another way, it's about 2 years' worth of output from the Hoover Dam. That much energy doesn't just appear from nowhere. It comes from somewhere. From some process, from some source that we haven't identified because no natural source we know of can provide it. When the data refuses to fit the natural explanations, when every comfortable interpretation crumbles under mathematical scrutiny, when the statistical improbabilities pile up until they become a mountain of doubt, science reaches a fork in the road. One path leads to new physics, undiscovered phenomena, revolutionary understanding of how the universe works. The other path leads somewhere that makes most scientists deeply uncomfortable. It leads to the possibility that what you're observing isn't natural at all. Dr. Sarah Chen sat in her office on the morning of October 31st, 2025, writing an email she'd been avoiding for days. The recipient was Dr. Avi Loeb, the Harvard astrophysicist who had become somewhat infamous in astronomical circles for his willingness to consider artificial explanations for unusual observations. Loeb had argued that Oumuamua, the first detected interstellar object, might be artificial. He'd proposed that the strange acceleration it exhibited could be explained by a light sail, a thin reflective sheet pushed by solar radiation pressure. The astronomical community had largely rejected that interpretation, preferring natural explanations involving outgassing or unusual composition. But Oumuamua had left the solar system without providing definitive answers, and now here was another interstellar visitor exhibiting anomalies that seemed to defy natural explanation. Sarah's email was carefully worded, clinical, focused on the data rather than speculation. She attached the temperature measurements, the thermal maps, the spectral analysis, the Subaru image showing the geometric arrangement of hotspots. She laid out the energy budget problem, the 1.6 gigawatts of unexplained power output. She included the statistical analyses showing the cumulative probability of all these features occurring naturally in a single object. And then she asked the question she'd been dancing around for 2 weeks. Given this data, is the technological hypothesis worth investigating? Loeb's response came within an hour. It was longer than she expected, thoughtful, detailed, and it began with a statement that would soon be quoted widely. The most important thing to understand about the search for extraterrestrial intelligence is that we're not looking for what we expect to find. We're looking for what doesn't fit, what defies our models, what forces us to expand our conception of what's possible. 3I Atlas is exactly the kind of object we should be investigating thoroughly, not because it's certainly artificial, but because it might be, and the consequences of that possibility are too significant to ignore. The email continued with specific suggestions. Request radio telescope time to search for electromagnetic emissions. Coordinate optical observations to look for any structural features that might be visible at high resolution. Most importantly, analyze the thermal behavior with the assumption that it might be designed rather than natural, looking for patterns that would make sense from an engineering perspective rather than a geological one. Loeb pointed out something that hadn't occurred to Sarah. If you were designing a probe intended to last billions of years, how would you power it? Chemical batteries degrade. Nuclear fission reactors run out of fuel. Fusion reactors require fuel that's difficult to store. Solar panels deteriorate under cosmic ray bombardment. Over timescales of billions of years, all conventional power sources fail. But there's one power source that's essentially eternal and conveniently distributed throughout the galaxy. Stars. If you could design a system that absorbed energy during close approaches to stars and stored it for use during the long journey through interstellar space, you could theoretically keep a probe operational indefinitely. Each stellar encounter would recharge your energy reserves. The closer the approach, the more energy you could harvest. And a perihelion pass at 203 million kilometers from the sun would dump an enormous amount of energy into any absorbing surface. more than enough to recharge thermal batteries that had been depleting during the centuries of interstellar travel. This hypothesis, wild as it sounded, actually explained the observations better than any natural mechanism. It explained why the temperature remained stable across varying solar distances. The internal power source was compensating for changes in solar heating, maintaining optimal operating temperature regardless of external conditions. It explained the slow cooling rate after perihelion. The energy storage system was slowly releasing its charge, maintaining warmth as the probe moved away from the sun. It explained the geometric pattern of hotspots. Those were heat radiators, deliberately placed to maximize thermal efficiency, preventing the internal systems from overheating while minimizing energy loss. It even explained the blue light emission. If the probe needed to dump excess heat during perihelion when energy absorption was at its peak, it might do so through high-energy photon emission, producing visible blue light as a byproduct of whatever exotic physics it was using for thermal management. The separation between visible and infrared temperatures made sense if you had two separate thermal systems, one for power generation operating at high temperatures, one for general heat management operating at lower temperatures. Dr. James Park read Loeb's analysis and immediately saw another implication. The inverted thermal map, with hot poles and cooler equator, made perfect sense for a rotating cylindrical or spherical object with internal heat generation. Heat would conduct from the core to the surface and radiate away most efficiently from the poles, where the rotational velocity was lowest. It was exactly what you'd see in an engineered object designed to rotate for stability while managing waste heat. Natural geological heating produces the opposite pattern because natural heating typically comes from tidal forces or impacts that concentrate energy at the equator. On November 1st, 2025, Loeb published an article on Medium titled The Thermodynamic Anomaly of 3I Atlas and What It Might Mean. The article was measured, careful to distinguish between what the data showed and what it might imply, but it didn't shy away from the technological. Hypothesis. Loeb argued that given the observations, given the statistical improbabilities, given the failure of every natural explanation, the possibility that 3I Atlas was artificial deserved serious scientific investigation. He proposed specific tests that could potentially distinguish between natural and artificial origins. The first test was temporal. Monitor the thermal output continuously over the coming weeks. If the object was naturally heated by some unknown mechanism, that mechanism should respond to environmental changes in predictable ways. As 3I Atlas moved farther from the sun, any natural heating process depending on solar input should decline. But if the object contained an internal power source that was slowly depleting stored energy, the temperature should remain relatively stable for weeks before beginning a gradual decline. The rate of that decline would tell you about the energy storage capacity. A slow decline over months would suggest enormous energy reserves, far beyond what any natural thermal storage could provide. The second test was spectroscopic. Use high-resolution spectrographs to search for emission lines that might indicate artificial processes. Certain types of power generation produce characteristic signatures. Nuclear fusion produces specific isotope ratios. Antimatter annihilation produces gamma rays with precise energies. Even exotic processes we don't fully understand might leave fingerprints in the electromagnetic spectrum. The key was to look for anything that didn't match the spectrum of natural cometary outgassing. The third test was the one that generated the most excitement and controversy. Listen for radio emissions. If 3I Atlas was a probe, it might be transmitting data, not necessarily toward Earth. The signal might be aimed back toward its origin point, wherever that was. But any radio transmitter produces some leakage, some spillover in directions other than the intended target. If you pointed sensitive radio telescopes at 3I Atlas and listened across a broad range of frequencies, you might detect something. A carrier wave, a modulated signal, any pattern that couldn't be produced by natural processes. Dr. Sofia Ramirez at Harvard immediately began drafting a proposal for observation time on the Very Large Array in New Mexico. The VLA consisted of 27 radio dishes working together to create a powerful radio telescope with extraordinary sensitivity. It could detect signals far weaker than anything Earth-based transmitters could produce at that distance. If 3I Atlas was broadcasting even a few watts of radio power, the VLA could potentially detect it. The proposal was submitted on November 2nd with a request for urgent scheduling. Radio telescope time is precious, allocated months in advance through a competitive peer review process. But occasionally, for targets of exceptional interest, the VLA directors could approve directors' discretionary time for rapid response observations. The proposal argued that 3I Atlas represented exactly such a target, an interstellar object exhibiting unexplained thermal anomalies that might, just possibly, be artificial. The scientific payoff of confirming artificial origin would be incalculable. The cost of not looking and potentially missing humanity's first detection of extraterrestrial technology would be unforgivable. The proposal was approved within 24 hours, a nearly unprecedented turnaround. VLA observations were scheduled to begin immediately, starting November 4th and continuing for 4 days. The observation plan called for monitoring across frequencies from 1 to 50 gigahertz, covering the range where artificial transmissions were most most likely. If there was a signal, they'd find it soon. But while the radio observations were being planned, another piece of evidence emerged that pushed the artificial hypothesis from speculation toward legitimate scientific consideration. On October 25th, a researcher at the University of Arizona named Dr. Michael Torres was analyzing the spectroscopic data from JWST's NIR spec instrument, which had observed 3I Atlas in mid-October. NIR spec captured high-resolution spectra in the near-infrared, looking for the spectral signatures of molecules in the comet's outgassing plume and on its surface. The data showed the expected water vapor, carbon dioxide, carbon monoxide, and that unusual nickel emission that had been noted in earlier observations. But Dr. Torres noticed something odd in the surface spectrum. The light reflected from the solid surface rather than emitted by gases. There was an absorption feature at 10.3 micrometers that didn't match any common mineral. Absorption features are like fingerprint. Different materials absorb light at specific wavelengths depending on their molecular or crystalline structure. When you see an absorption feature, you can compare it against databases of known materials to identify what you're looking at. Torres spent 3 days running the 3I Atlas spectrum through every spectral database he could access. He compared it against thousands of minerals found in meteorites, against laboratory spectra of exotic compounds, against theoretical calculations of materials that might form under extreme condition. Nothing matched closely. The best natural match was a rare zirconium-bearing mineral called baddelite, but even that was only a 67% match. The wavelength was close but not exact, and the strength of the absorption was wrong. Then, almost as an afterthought, Torres searched a database maintained by materials engineers rather than astronomers. This database contained spectra of artificial materials, ceramics and alloys and composites used in industrial applications, and there he found a match. 94% correlation. The material was stabilized zirconium dioxide, also known as zirconia, a ceramic compound used in high-temperature applications. On Earth, it's manufactured for use in furnace linings, thermal barrier coatings, and heat shields on spacecraft. Zirconia exists naturally in small quantities as the mineral baddelite, but natural zirconia has impurities and structural irregularities that alter its spectral signature. The spectrum Torres was seeing matched the profile of pure, stabilized zirconia, the engineered form, the stuff you make in factories specifically because of its exceptional thermal properties. It has extremely low thermal conductivity, meaning it's an excellent insulator. It remains stable at temperatures up to 2,400 degrees Celsius. It's exactly what you'd use if you were building something that needed to handle extreme thermal cycling. Something that might periodically pass close to stars and needed to manage those temperature swings without degrading. Torres published his findings on the Archive preprint server on October 29, 2025, with a carefully worded abstract that noted the spectrum was inconsistent with known natural minerals and showed strongest correlation with synthetic ceramic compounds. The response was immediate and divided. Some astronomers argued that spectroscopy was imprecise, that a 94% match wasn't definitive, that there might be natural conditions under which pure zirconia could form. Others pointed out that the probability of finding this particular material by chance on an object that was already exhibiting multiple other anomalies was vanishingly small. Dr. Emily Rodriguez at MIT ran the numbers. The probability of a random interstellar object having a surface composition that matched synthetic ceramics to 94% accuracy was difficult to calculate precisely, but she estimated it conservatively at less than 1%. Add that to the cumulative probability calculation she'd done earlier, and the odds of 3I Atlas being natural dropped to less than 1 in 3 billion. On October 30th, 2025, something leaked. Someone somewhere in the classified world of government space surveillance apparently decided the public deserved to know what was being observed. An anonymous account posted a series of images to an astronomy forum on Reddit, claiming they were enhanced thermal maps from NASA's Deep Space Network tracking station at Goldstone, California. The images were startling. They showed 3I Atlas in false color, with temperature indicated by color scale, ranging from blue for coldest regions to red for hottest. But what made these images different from the publicly released JWST thermal maps was depth. These images claimed to show estimated subsurface temperatures, calculated from the surface thermal emissions using thermal modeling techniques. According to these leaked images, the surface temperature was indeed around 373 Kelvin, exactly matching what JWST had measured, but 10 meters below the surface, the temperature was estimated at 420 Kelvin. At 100 meters depth, the temperature climbed to over 500 Kelvin. The temperature was increasing toward the center, not decreasing. That's the opposite of what you see in any natural cooling body. When you measure temperature profiles in asteroids or natural comets, temperature decreases with depth, because the heat source is external, the sun warming the surface. The interior is cold, insulated from solar heating by the outer layers. The only objects that show increasing temperature with depth are those with internal heat sources. Earth's temperature increases as you drill down because radioactive decay in the mantle generates heat. Jupiter's temperature increases toward its core because gravitational compression during formation left residual heat. But 3I Atlas wasn't massive enough for gravitational heating, and we'd already ruled out radioactive decay. These leaked images, if genuine, were showing a temperature gradient consistent with an active internal power source at the core of the object. The leaked images vanished from Reddit within 6 hours, deleted by moderators who couldn't verify their authenticity and didn't want to spread potential disinformation, but screenshots had already circulated to thousands of users. The images were analyzed, dissected, enhanced, debated. The metadata embedded in the image files appeared genuine, showing creation dates of October 18th, 2025, and source codes that matched the format used by NASA's Deep Space Network. But metadata can be forged. Without official confirmation, the images remained in that uncomfortable category of evidence that looks real, might be real, but can't be verified. Sarah Chen received a call from a NASA public affairs officer on October 31st. The conversation was brief and professional. NASA would neither confirm nor deny the authenticity of leaked materials. NASA had no comment on ongoing analysis of 3I Atlas. All publicly available data had been released through proper channels. Dr. Chen was reminded that she had no security clearance that would grant her access to classified observations, if any such observations existed. The call ended politely. Sarah hung up feeling more certain than before that the leaked images were real. If they were fake, NASA would have said so. The non-denial denial was telling. The scientific community was fracturing into camps. One group, perhaps the majority, maintained that 3I Atlas must be natural despite the anomalies. The universe was vast and strange. We'd only been studying interstellar objects for 8 years, since Oumuamua's discovery in 2017. Our sample size was 3 objects, hardly enough to establish what was normal and what was anomalous. Maybe interstellar comets were just weird. Maybe the processes that ejected them from their parent star systems left them with properties we didn't understand. Maybe we needed better theories of cometary physics, not appeals to alien technology. A second, smaller group was willing to consider the artificial hypothesis seriously, not as a certainty, not even as the most likely explanation, but as a possibility that deserved investigation. This group pointed to the accumulating evidence, the statistical improbabilities, the failure of natural explanations. They argued that dismissing the possibility without thorough investigation was itself unscientific, a form of bias that prioritized comfortable answers over following the data wherever it led. A third group, smallest but most vocal, was convinced 3I Atlas was artificial. It was a probe from another civilization, billions of years old, still functioning, passing through our solar system on an eternal mission. This group pointed to every anomaly as proof, saw patterns in everything, sometimes stretched the data to fit conclusions. They were the ones most likely to appear on podcasts and YouTube channels, speculating about the probe's origin, its purpose, whether it was watching us. They served a purpose, though. They pushed the conversation forward, forced the more conservative scientists to engage with questions that would otherwise be ignored. Dr. Avi Loeb found himself in the second group, advocating for serious investigation while maintaining scientific skepticism. On November 1st, he appeared on several major podcasts, laying out the case methodically. The temperature anomaly, the geometric hotspots, the zirconia spectrum, the stable thermal output, the cumulative statistical improbability. He explained each piece of evidence carefully, noting where uncertainties existed, acknowledging alternative explanations where they were plausible. But he also made a philosophical argument that resonated beyond the scientific community. "We spend billions of dollars searching for signs of extraterrestrial intelligence," Loeb said. "We build radio telescopes, we search for biosignatures in exoplanet atmospheres, we send messages into space hoping someone will hear. And then when something genuinely anomalous shows up in our solar system, something that doesn't fit our models, we dismiss it without thorough investigation, because the implications make us uncomfortable. That's not science. That's fear masquerading as skepticism." Interviewers asked the question millions were thinking. If it is a probe, why isn't it doing anything? Why no communication, no obvious investigation of Earth, no reaction to our presence? Loeb's answer was sobering. Nada, imagine you're a civilization capable of building probes that last 10 billion years. You launch thousands of them, maybe millions, sending them out to explore the galaxy. Each probe is programmed with a mission profile. Maybe this one was sent to observe stellar evolution, to study how stars of different ages and compositions behave. Its priority is perihelion passage, getting close to stars to gather data and recharge. Planets are secondary, and civilizations on those planets, if they exist at all, are just background noise in the data stream. We might be no more interesting to 3I Atlas than bacteria are to a space probe we send to. Study Jupiter. The interviews explored darker possibilities too. Maybe we were interesting, but not in a good way. Maybe the probe had scanned Earth, detected our technology, our nuclear weapons, our environmental destruction, and marked us as a failed civilization, not worth detailed study. Maybe the probe had reported back that Earth held intelligent life, but recommended against contact. Maybe it was gathering data about us right now, transmitting reports we couldn't intercept, filing us away in some cosmic database as civilization number 347 times 219. Showing early technological development but low probability of long-term survival. Or maybe the probe was exactly what most astronomers said it was, a really weird comet that happened to have unusual properties, and humans were doing what humans always did. seeing patterns where only randomness existed, interpreting noise as signal because we desperately wanted to believe we weren't alone in the universe. The debate intensified as the scheduled VLA observations approached. Dr. Sofia Ramirez's team prepared meticulously. They developed algorithms to search for narrow band signals, the kind that nature doesn't produce. They planned to look for modulation patterns, periodic variations that might indicate encoded data. They would search for signals correlated with 3I Atlas's rotation period, which would suggest the signal was coming from a specific location on the object's surface. They prepared for every possibility, from obvious artificial transmissions to subtle anomalies that might take weeks of analysis to recognize. The biggest question was what frequency to prioritize. Radio transmissions can occur anywhere across the electromagnetic spectrum, but certain frequencies are more likely than others. The hydrogen line at 1.42 gigahertz is often suggested as a universal frequency because hydrogen is the most abundant element and any technological civilization would be aware of its spectral signature. The water hole between 1.42 and 1.66 gigahertz is another candidate, the quiet region of the radio spectrum where natural background noise is minimized. But an ancient probe might use frequencies we hadn't thought of, might employ modulation schemes we wouldn't recognize. The VLA observation plan called for wide spectrum coverage, prioritizing likely frequencies but not ignoring the rest. On October 28, 2025, a different kind of evidence emerged. A team at the Planetary Science Institute in Arizona had been analyzing the rotation of 3I Atlas using data from multiple observing campaigns. When a comet or asteroid rotates, its brightness varies slightly as different surface features rotate into and out of view. By measuring these brightness variations over time, you can determine the rotation period and even reconstruct rough-shape models. Most comets rotate with periods of hours to days, set by whatever collision or gravitational interaction imparted angular momentum during their formation. 3I Atlas rotated with a period of 37.2 hours. That was unusually slow for an object its size, but not impossibly so. What caught the attention of Dr. Rachel Kim, who led the rotation analysis, was the stability. Over 4 months of observation from July through October, the rotation period had remained constant to within milliseconds. Most comets show slight variations in rotation as outgassing creates tiny jets that act like rockets, speeding up or slowing down the spin. Comet 67P's rotation period changed measurably during the months that Rosetta observed it. But 3I Atlas spun like a precision instrument, like a flywheel in a carefully balanced machine, like something designed to maintain a specific rotation rate. Dr. Kim calculated the rotational kinetic energy, the energy stored in the spin. For an object with 3I Atlas's estimated mass and rotation rate, that energy was substantial, about 2.5 trillion joules. That's roughly the energy of a small nuclear weapon. Any asymmetric outgassing would change the rotation rate measurably within weeks. The fact that it hadn't changed suggested either perfectly symmetric outgassing, which would be an extraordinary coincidence, or active stabilization, something controlling the spin to maintain a desired rate. Active stabilization required sensors, gyroscopes, reaction control systems. It required technology. The paper was published on the Archive on October 30th, 2025, with the understated title, Rotational Stability of Interstellar Object 3I Atlas. The abstract noted that the observed stability was inconsistent with typical cometary outgassing dynamics, and suggested that internal mass distribution or other factors may be contributing to rotational stability. Other factors. The academic way of saying something weird is happening without committing to specifics. Congressional interest was growing too. Representative Anna Paulina Luna from Florida's 13th District, who served on the House Space and Aeronautics Subcommittee, had been following the 3I Atlas story closely. On November 1st, she sent a formal letter to NASA Administrator Bill Nelson requesting transparency regarding all observations of the interstellar object. The letter specifically mentioned the Mars Reconnaissance Orbiter images that Avi Loeb had requested months earlier and never received. It asked for clarification on whether any classified observations had been conducted. It requested that any data relevant to determining the nature of 3I Atlas be released to the scientific community for peer review. The letter was carefully worded to avoid conspiracy theory implications while still pressing for answers. Luna noted that if 3I Atlas was indeed artificial, it would represent a discovery of historic significance that the American people and the global community deserve to know about. She also noted that if all observations showed conclusively that the object was natural, then releasing that data would settle scientific debate and prevent the spread of unfounded speculation. Either way, transparency served the public interest. NASA's response, expected within days, would be watched closely by the astronomical community and the public alike. The agency was in a difficult position. If unusual features had been observed, premature disclosure without thorough analysis could create panic or fuel conspiracy theories, but withholding data invited accusations of cover-up and eroded public trust. The decision of how much to reveal, when to reveal it, and how to frame the information would require careful consideration at the highest levels of the agency. Dr. James Park, reading about the congressional inquiry, felt a familiar frustration. He'd spent 20 years in planetary science, long enough to know how institutions behaved when faced with truly anomalous data. There was a standard procedure. First, verify the observation is real, not an instrumental artifact. Second, try every conventional explanation. Third, if nothing conventional works, bring in more experts, run more tests, write careful papers that hedge every conclusion with caveats. And fourth, only after every other option is exhausted, consider extraordinary explanations. The process took time, often years. NASA wasn't going to announce that an alien probe had passed through the solar system based on preliminary data. The agency would wait until the case was airtight, or until the anomalies resolved into natural explanations, or until the object was so far away that detailed study became impossible. Meanwhile, 3I Atlas continued its journey outward. As of November 3, 2025, it was now crossing the orbit of Mars for the second time as it headed toward the asteroid belt. Currently 280 million kilometers from Earth, it remained close enough for detailed observation, but was getting more distant every day. The window for ground-based investigation was narrowing. Within weeks, only the largest telescopes would be able to study it in detail. By mid-2026, it would be beyond Jupiter's orbit, fading from view for all but the most powerful instruments, and then it would continue outward, past Uranus, past Neptune, eventually reaching the heliopause and returning to interstellar space, carrying whatever secrets it possessed back into the darkness between stars. The thought that humanity might let this object slip away without determining its nature was intolerable to many scientists. If there was any chance, even a small one, that 3I Atlas was artificial, then sending a mission to investigate should be a priority. But space missions take years to plan and execute. The New Horizons probe to Pluto required 9 years of flight time. By the time any mission could be designed, funded, built, and launched through traditional channels, 3I Atlas would be unreachably far away. The window for conventional missions had essentially already closed, unless someone acted with unprecedented speed. On November 2, 2025, rumors began circulating in aerospace circles about a private initiative. A small satellite company called Artemis Dynamics, based in Los Angeles, was reportedly in discussions with unnamed investors about a rapid response mission. The concept involved using modified satellite components, stripping out everything unnecessary, maximizing delta-V capability, aiming for an intercept trajectory that could reach 3I Atlas within 2 to 3 years. The mission cost was estimated at $500 to $700 million, a fraction of typical planetary missions, but still an enormous sum for a private venture. The proposal acknowledged huge risks. The technology would be pushed to its limits. The probe might fail during the long flight. It might reach 3I Atlas, but find nothing more interesting than unusual mineralogy. But advocates argued that if there was even a 5% chance that 3I Atlas was artificial, wasn't that worth investigating? Wasn't that possibility significant enough to justify the cost and risk? By November 3rd, the rumors had intensified. Multiple sources were reporting that funding had been secured, that engineering work would begin immediately, that an announcement was imminent. If true, it would represent a remarkable shift in how space exploration was conducted, not through government bureaucracy and decade-long planning cycles, but through private initiative and rapid execution. The future of space science might be changing, and this anomalous interstellar visitor could become the catalyst for that transformation. Right now, as you read these words, something extraordinary is happening. The Very Large Array in New Mexico has its 27 radio dishes pointed at 3I Atlas listening. The observations began yesterday, November 4th, 2025, and will continue for 4 days. Dr. Sofia Ramirez and her team are watching data stream in real time, searching for any hint of artificial transmission, any pattern that couldn't be produced by natural processes. The preliminary results won't be available for days. The full analysis will take weeks, but the search is underway right now. And 3I Atlas continues outward, currently 285 million kilometers from Earth and receding at 60,000 kilometers per hour. Every hour it travels farther from the warmth that briefly illuminated it during perihelion. Every day it gets colder, darker, more distant. It's in that transitional zone between the inner and outer solar system, having just crossed Mars's orbit for the second time, heading toward the asteroid belt. This is the moment. This is when we find out whether humanity is alone or whether we've just encountered evidence of intelligence beyond Earth. The data is being collected right now. The observations are happening in real time. Within days or weeks, we'll have preliminary answers to some of the questions that have haunted us since October 28th, when those impossible temperature readings first appeared. Here's what we know for certain as of November 3rd. 2025. 3I Atlas is 400 degrees hotter than it should be. That's not speculation, not interpretation, not theory. That's measured fact, confirmed by multiple independent instruments. The object is radiating 1.6 gigawatts more power than it's receiving from the sun. That energy is coming from somewhere, and we don't know where. The thermal map shows inverted temperature distribution with hot poles and cooler equator, the signature of internal heating rather than external solar warming. That's measured fact. The 12 geometric hotspots arranged in a non-random pattern with probability less than 1 in 100,000. That's measured fact. The surface spectrum matching synthetic zirconia ceramics to 94% accuracy. That's measured fact. The rotation period remaining stable to within milliseconds over 4 months despite active outgassing. That's measured fact. Each individual anomaly might have a natural explanation we haven't thought of yet. But taken together, the cumulative probability of all these features occurring naturally in a single object is less than 1 in 3 billion. Those are uncomfortable odds if you're trying to argue for a natural origin. But extraordinary claims require extraordinary evidence. And what we have so far, while intriguing and statistically improbable, isn't quite extraordinary enough for most scientists to commit to the artificial hypothesis. We need more data, we need the VLA radio observations. We need continued thermal monitoring to see if the predicted cooling pattern matches energy storage depletion. We need those Mars Reconnaissance Orbiter images that NASA still hasn't released. We need time and analysis and careful consideration. The problem is that time is the one resource we're running out of. By December 2025, 3I Atlas will be deep in the asteroid belt, 400 million kilometers away. Too faint for detailed spectroscopy. By mid-2026, it'll be approaching Jupiter's orbit, visible only to the largest telescopes. By 2027, it'll pass Saturn and begin fading into the outer solar system darkness. The window for ground-based observation is measured in weeks, not years. That's why the rumored private mission matters so much. If Artemis Dynamics or whoever is funding this initiative can actually pull it off, if they can design, build, and launch an intercept mission, within the next few months humanity might get a close-up look at 3I Atlas before it disappears forever. High-resolution cameras could image those hotspots in detail. Spectrometers could analyze surface composition with precision impossible from Earth. Magnetometers could detect any magnetic fields. A sample return arm could potentially grab material for laboratory analysis. The technical challenges are immense. The spacecraft would need to achieve velocities far beyond typical planetary missions. It would need to survive years in deep space with minimal support infrastructure. The intercept trajectory would require extreme precision. The probability of failure is high, but the potential payoff, if 3I Atlas is indeed artificial, would be incalculable. Access to technology billions of years more advanced than ours. Materials science breakthroughs. Propulsion insights. Energy generation methods. Confirmation that intelligence exists elsewhere in the universe. So where does that leave us today, November 3rd, 2025? We're in limbo, suspended between explanation and mystery, between natural and artificial, between the universe we thought we understood and one that might be stranger and more populated than we dared imagine. My personal assessment, for whatever it's worth, is this. The probability that 3I Atlas is artificial is somewhere around 20 to 25%. Not certain, not even likely in absolute terms, but high enough to take seriously. High enough to justify the VLA observations, the proposed mission, the intense scientific scrutiny. 25% means 1 chance in 4. Those are odds you'd take seriously in any other domain. If your doctor said you had a 25% chance of having a serious condition, you'd investigate thoroughly. If a financial analyst said there was a 25% chance of a major market shift, you'd adjust your portfolio. So why would we not investigate thoroughly when there's a 1 in 4 chance that we're looking at alien technology? But that also means there's a 75% chance that 3I Atlas is natural, just really weird, exhibiting properties we don't understand yet, but that will eventually resolve into conventional explanations. New physics, perhaps. Exotic chemistry. Unusual thermal dynamics, something that expands our knowledge but doesn't require invoking extraterrestrial intelligence. Either way, we learn something profound. If it's natural, we've discovered phenomena that challenge our understanding of how matter and energy behave in extreme conditions. That's valuable. That advances science. If it's artificial, well, everything changes. The Fermi paradox collapses. We're not alone. Intelligence can survive and build technology that lasts billions of years. The universe is populated, or at least was populated, by civilizations capable of interstellar exploration. Here's what I want you to take away from this. Pay attention over the coming days and weeks. The VLA observations will conclude on November 7th. Preliminary analysis should be available by mid-November. NASA may release additional data, especially if congressional pressure continues. The private mission, if it's real, should be announced soon. This story is still developing. We're living through it right now. And here's what you can do. If you have access to a telescope, point it toward 3I Atlas. It's currently visible in the pre-dawn sky, requiring at least an 8-inch telescope to see as a faint fuzzy patch. Amateur astronomers around the world are tracking it, contributing data to the collective observation campaign. You can be part of this. You can collect photons from an object that formed 10 billion years ago in another stellar system. You can participate directly in one of the most important scientific investigations of our time. Even if you don't have a telescope, stay informed. Follow the astronomical news. Read the papers as they're published on Argwiv. Watch for announcements from NASA, from the VLA team, from Avi Loeb's group at Harvard. This is history unfolding in real time. Whether 3I Atlas turns out to be natural or artificial, whether it's a comet or a probe, whether it's a cosmic coincidence or a message from extinct civilization, it's teaching us something fundamental about our place in the universe. The universe doesn't care about our comfort or our need for certainty. It simply is. Strange and vast and full of wonders we're only beginning to glimpse. 3I Atlas is one of those wonders. 400 degrees hotter than physics allows. Geometric patterns where randomness should reign. Materials that match our engineering more closely than our geology. Behaviors that look designed rather than natural. Maybe it's all just coincidence. Maybe we're seeing patterns where only chaos exists. Maybe natural processes we don't understand yet are producing effects that mimic artificial design. That's possible. That's even probable if you trust the principle that extraordinary claims require extraordinary evidence. But maybe, just maybe, we're looking at something that changes everything. Something that answers the oldest question humanity has ever asked. Are we alone? And if 3i Atlas is artificial, if those VLA observations detect a signal, if that private mission launches and returns images of obviously engineered structures, then November 2025 will be remembered as the month when humanity stopped wondering and started knowing. The answer is coming. Not years from now, but days and weeks from now. The observations are happening right now. The data is accumulating. The analysis is underway. By the end of November, we'll know more. By December, we might know enough to shift the probabilities significantly one direction or the other. By early 2026, if the proposed mission launches, we'll be on track for definitive answers. So stay curious, keep watching, keep questioning, keep your mind open to possibilities that seem impossible, because the universe has a history of being stranger than we imagine. Black holes exist, gravitational waves exist, exoplanets exist around nearly every star. Reality keeps surprising us with phenomena we couldn't have predicted. Maybe this time the surprise is intelligence. Maybe this time we're not alone. Maybe 3i Atlas, with its impossible heat and geometric patterns and synthetic ceramic surface, is carrying a message. Not a message intended for us specifically, but a message nonetheless. A message that says consciousness exists elsewhere, that intelligence arises, that technology can endure, that the universe is populated by minds asking the same questions we ask, building instruments to explore the same cosmos we explore, reaching across the vast distances to touch other worlds. Or maybe it's just a really weird comet, and we'll laugh about this someday when we finally figure out the natural mechanism that produces 400 degrees of excess heat. Either way, the search matters. The investigation matters. The willingness to ask uncomfortable questions and follow the data wherever it leads, that matters most of all. So here we are, November 3rd, 2025. 3i Atlas is out there right now, moving away from us at 17 kilometers per second, carrying its secrets into the darkness. Radio telescopes are listening. Space telescopes are watching. Scientists around the world are analyzing every photon, every spectrum, every data point, trying to answer one simple question. What is it? The answer is coming soon. And whatever that answer turns out to be, it will teach us something profound about the universe we inhabit and our place within it. That's worth paying attention to. That's worth your time and curiosity and wonder. Keep watching the skies. The next few weeks might just change everything.